Okay, so ladies and gentlemen, I have a pleasure to give another presentation today about evaluation of prosthetic socket design using finite element analysis. As was mentioned before, my name is Agata Mrozek and I work in Bootsoft as simulation engineer. I've divided my presentation into 4 sections. I would like to start with the short introduction to the topic of lower limb prosthetics and outline the potential benefits of using finite element analysis in prosthetic socket design. Next, I will present the applied finite element model of prosthetic socket donning, and I will sum up with short conclusions. So firstly, let me give you some background information. Amputation is the surgical removal of damaged extremities, and many types of amputation or levels of lower limb extremity can be distinguished, but they can be generally presented as the following amputation level. So hip disarticulation. Disarticulation means performing amputation at joint level. Transfemoral amputation, knee disarticulation, transtibial amputation, and foot amputation. The level of amputation determines the number of components in the lower limb prosthesis. Nevertheless, in most cases, one of the most essential parts of the prosthesis from the point of view of patient safety and comfort is prosthetic socket. And in this presentation, we will focus on transfemoral amputees. For lower limb extremity amputees, prostheses are commonly used to restore mobility and foster return to normal physical activities. Lower limb prostheses are generally developed with 3 main parts: the socket, the pylon, and, the prosthetic foot. Often, then consists also of an artificial knee system. In case of prosthetic foot, pylon, or knee system, they are prefabricated components and they must be adjusted to the patient. But a critical component of the prosthesis is the prosthetic socket. Typically, lower limb prosthesis needs a socket to act as an interface or link between the residuum and the prosthetic device. And this situation modifies completely the natural performance of the residual limb. The most important physiological change is suffered by the soft tissues that transfer the body load generated during the gait. And this new condition can induce skin problems and can also affect the vascular system. The interface pressure between the residual limb and the prosthetic socket significantly affects patient comfort. Due to the individual anatomical shape of the residuum, it requires a high level of customization. And in conventional procedure, fitting prosthetic is an iterative process, and the finite element analysis delivered tools which enable to evaluate interface pressure between the residual limb and prosthetic socket and validate the socket shape. So this will allow to speed up the design process of prosthetic socket. Socket donning apply press stresses to the residuum tissues. The key issue during simulation is to resolve the difference in the shapes between the limb and the press fit socket. So in this presentation, explicit donning is simulated. The socket is moved into a small initial contact with the limb, and small overclosure step is resolved to give numerical stability, and it's followed by sliding the socket onto the limb and calculating generated interface stresses. The finite element model consists of 3 parts: residuum limb, cutted bone, and prosthetic socket. Patient-specific geometry is obtained using CT and MRI data. This information includes bone and its relative position to the soft tissue. Sometimes the residuum limb geometry is obtained using laser scanner data. Since the sockets are custom-made, it is important to include as many patient-specific features like surgical scars as possible. And after obtaining patient-specific data, the individual prosthetic sockets are designed using CAD software. So it is possible to identify the initial overclosure between the soft tissue and the socket, which will be solved during the numerical simulation of the socket donning procedure. Socket was designed with the press fit. It means that there is a cross-sectional area reduction. The donning procedure was simply simulated explicitly because a simplified overclosure method where the socket are fixed in assumed position and residuum external surface is displaced until in contact with the internal surface of the socket. It's not real in this situation, and we didn't receive appropriate shear stresses. In this study, a linear elastic homogeneous isotropic condition of the bone was considered, while for prosthetic socket elastoplastic material model was used. For the soft tissues, hyperelastic condition was used using Money-Rivlin solid strain energy function, and average flaccid muscle was selected as the baseline, and the material properties were obtained from the literature. The interaction between the bone and the soft tissue was modeled using a tight condition that simulate the perfect bonding between two materials. The interaction between socket and the stump was modeled using general contact condition. And taking into account that during the donning procedure, the amputees used some kind of sock to insert stump into socket, a friction coefficient was assigned to a contact. The applied boundary condition are shown on the slide. The hip joint action was represented with a restriction on all degrees of freedom relative in the femoral head. Before the simulation, the socket and the stump were not in contact, and during the simulation, the displacement vector of the proximal part of the socket was applied. The value of this vector is equivalent to the displacement that it's needed to put the stump in the actual final position within the socket. And the displacement applied to the socket was made in the quasi-static step, where the velocity needs to be as low as possible to minimize the dynamics effect, but using a reasonable time of calculation. And approximately velocity was 6 mm per second. The application of finite element analysis enable us to simulate the different activities performed by patient. For example, jumping, walking, distinguishing different gait phase like heel strike, mid stance, or toe off analysis. And in the second step of this analysis, following simulation of the donning procedure, the load case used was a surface traction load, which represents the 300 newtons, and it represents double leg stance. Due to the complexity of geometry, tetrahedral elements were used for all parts, and applied element type was C3D10, and for residuum limb, the applied elements were hybrid. Let's now move to the obtained results. Conducted analysis enable us, first of all, to assess the stress state in the prosthetic socket. The highest value of stresses was observed on the surface which penetrates the residuum in order to provide a press fit condition, and the highest value of obtained stress was equal to 0.2 megapascals. Knowledge of the pain threshold and tolerance of the soft tissue around the residual limb is needed for the improvement of comfort in prosthetic use. It reflects the magnitude of pressure that can be applied by the prosthetic socket without causing discomfort and intolerable pain. The map presented on the slide considered the contact pressure obtained for donning procedure, and the highest value of obtained contact was about 8 kilopascal, which is significantly lower than the pain threshold. The maximum was observed at the surface, which was designed to provide initial press fits. Longitudinal shear stress in Pascal are shown on the slide. The models using simulation donning procedure represent more accurately the actual donning procedure, where the relative displacement between socket and the stump generate not only normal stresses, but also shear stresses. The longitudinal shear stresses achieved a value of 3.5 kilopascal during donning procedure. Circumferential shear stresses are shown on the slide, and the evaluation of shear stresses are important from the point of view of prosthetics. Prosthesis' aim is to achieve limited socket residuum shear load transfer to protect residuum distal tip from the end bearing while avoiding excessive shear that might increase the risk of, for example, skin breakdown. As such, accounting for different sources of shear loading in the model is one of the particular importance for the clinical transfer. After donning procedure, the socket was loaded in order to represent the double leg stand space. The obtained stresses after loading achieved a value of 0.26 megapascal, and the highest stressors were observed in the cross-section, in the area of cross-section reduction. It was also observed on the distal tip of the prosthetic socket. But the value of obtained stress was significantly lower than the yield strength of the applied materials. The obtained results after selected activities enable us not only to evaluate the durability of the prosthetic socket, it also enables to indicate the area of prosthetic socket which have to be corrected. For example, as shown in the slide, during this double leg stand phase, the highest value of the contact pressure, 31.5 kilopascal, was observed at the distal tip of residuum lip, which is sensitivity area. Presented workflow enabled to analyze and compare different design of prosthetic socket in different loading conditions. Nevertheless, there is another significant variable in the field of prosthetic sockets on which we will focus in this part of presentation. So, changes in residual limb volume and shape lead to the problems with creating and maintaining an accurate and comfortable fit of the prosthetic socket. In the mature residual limb, both the daily and long-term changes over weeks or months can occur. Shape and volume changes in the residual limb are believed important to changes in limb socket interface pressure and shear stresses distribution, which may in turn lead to the socket fit problems, including gait instability or skin breakdown. So, based on the obtained information, the changes could reach a value of even 10%. It results in more severe differences in the shape of socket at residuum limb. For example, the example of volume changes and their influence on the initial overclosure are shown on the slide. And the analysis was conducted for assumed level of changes, 5% and 10%. On the slide, there is a view on the contract pressure map for both cases. The bigger the changes of the volume, the patient is more likely to experience discomfort. In the base case, the area in which the highest value of contact pressure was observed was the spot specially designed in order to obtain the press-fit socket. For the residuum after the increase in their volume, the highest value was observed for upper edges of the socket sliding on the residuum surface. The observed changes has a significant impact not only at the area of maximum contact pressure, but also on the obtained value. Increase of 10% in the value of residuum results in increase in the value of maximum contact pressure equal to 80%. So to conclude, let me sum up my main points. The interface pressure between the residual limb and prosthetic socket significantly affects the patient comfort. The finite element analysis delivered tools which enable to evaluate the interface pressure between the residual limb and prosthetic socket and validate the socket shape. This will allow to speed up the design process of prosthetic socket. Including explicit simulation of donning procedure enables to consider the shear stresses which are relevant from the point of clinical view. Application of finite element analysis and able to improve general understanding on how differences in residual limb shape and prosthetic shape design affect patient comfort and clinical outcomes. And evaluation of prosthetic circuit design using finite element method enable to compare comparative assessment of wide range of prosthetic circuit design. Thank you for your attention. If anyone have any question, please write it on the chat and I will be glad to answer any question you might have.